Ryan, and this is Jonathan, and welcome to Concavity. Concavity is the way a graph curves upward or downward. The graph of a differentiable function is concave upward on an open interval when the derivative is increasing on the interval. The graph will concave downward if the derivative is decreasing on the interval. Open intervals on which the graph of a function f is concave upward or downward. You need to find the intervals on which f prime is increasing or decreasing.
For instance, the graph of f of x equals 1/3 x cubed minus x is concave downward on the graph interval negative infinity and 0 because f prime of x equals x squared minus 1 is decreasing.
For concavity, you need the following theorems. Let f be a function whose second derivative exists on a point on open interval I. If f double prime of x is greater than 0 for all x in I, then the graph of f is concave upward in I. If f double prime of x is less than 0 for all x in I, then the graph of f is concave downward in I. To apply theorem, locate the x value at which f double prime of x equals 0. Or it doesn't exist. Second, use these x values to determine the test intervals. Finally, test the sign of f double prime x in each of the test intervals.
Yeah. Example to determine concavity is f of x equals x cubed minus 9x squared plus 8x minus 5. First, you derive the function, which equals f of prime of x equals 3x squared minus 18x plus 8. This gives you the slope and the extremus. Second, you derive the derived function f prime, which equals f double prime of x equals 6x minus 18. This gives you the concavity and points of inflation. This is called second derivative test. Then you find the intervals that can be plugged into the equation equal to 0. The numbers that you use to equal 0 are called critical numbers. Critical numbers allow you to determine if a function is concave up or concave down. To use critical numbers, you first have to see if the problem gives you endpoints, for example, 4 and 12. Otherwise, use infinity as your endpoints. Once you find the critical numbers, you have to make intervals.
Inflection, which is when the slope changes, you have to find out when the intervals are concave up and concave down. The critical number where the function changes from concave up to concave down or from down to up is used in the point of inflection if both intervals are concave up or concave down.
Then there is no point of inflection. Once you find the critical numbers where the concave changes, you plug it back into the original function f of x.
Concavity appears in our everyday lives. Roller coasters are the easy examples. It shows every form of concavity and is extremely fun.